It's my It is my great pleasure to introduce Jeff Galkowski. He will be speaking about geodesic beams and bioreminders.
Thank you to all the organizers for the invitation to speak sort of in Argentina. I've only been to South America once before, so hopefully more times in the future. And so as Shiza said, who's my collaborator on this work, I'll be speaking about geodesic beams and bioreminders. And so I want to just start by reminding everyone or telling everyone what the sort of setting is going to be. And in particular, I'm going to be working on a smooth compact Riemannian manifold without boundary. And I'm going to be thinking about one of the classical questions in this area, which is, okay, so I have the Laplace-Beltrami operator on this manifold. It has a nice discrete sequence of eigenvalues tending off to infinity, and you want to know asymptotics for this number of eigenvalues below a certain lambda. So just like Josef was talking about for the Steklov problem, sort of spectral asymptotics, of course, is a classical question for the Laplace-Beltrami operator, perhaps less classical for the Steklov problem, but has now received a great deal of interest. And so this is maybe the original question of Weil, which is how many eigenvalues, or maybe, okay, that Weil answered, which is how many eigenvalues are less than a certain lambda. And the answer is sort of known now, which is that it's given by some kind of volume on the manifold times lambda to the n plus an error. And the question is, what is the error, or is this really an asymptotic? And okay, so I like the story, so I'm going to tell it again. So, you know, Hilbert raised this question in the early 1900s. I don't remember exactly the year. He said, you know, this is what I think the answer is. This is the main term plus an error. And he said, but I don't think it'll be proved in my lifetime that it's true. But the next year, Weil actually proved this thing, and you know, everybody was happy that they all survived to see it. So then afterwards, so that was a small o of this main term, just to say that this is the main asymptotic term, but then a huge amount of work went into this subject. And the sort of sharp result in this case is that this error is lambda to the n minus 1, and that was proved by Levitin, Abakumovich, and Hormander. And the reason, you know, Hormander is, even though he was sort of quite a lot later, is often quoted here, is that he really developed a framework for handling this problem using microlocal techniques. And it's not hard to check that on the sphere, this remainder is in fact optimal. You have multiplicity of the size of this remainder, and so you cannot beat this remainder in general. Moreover, even if the manifold is only Zoll, not really exactly a sphere, but nevertheless has periodic geodesic flow, you can check that you cannot beat this remainder. And so you of course might ask yourself, when can this be improved, or can it be improved in any situation, now that you know it's sharp? And so the sort of most classical place where this is true is the case of manifolds where the set of periodic trajectories has zero Liouville measure, I should say, in the cosphere bundle. And that goes back to Duistermaat and Gilman in the 70s. And I mention Ivry here because he of course proved this in the case of a manifold with boundary, which was a major breakthrough in the subject in the 80s. And there you have, of course, an extra term coming from the boundary. Now, this is a nice condition, right? Which it's sort of checkable. You can ask yourself, given a manifold, you can try to check whether this manifold is periodic or not. But it doesn't tell you, you know, a lot about the quantitative asymptotics of the counting function. And so one instance of this where this is relatively easy to check is that of the product manifolds. So there you have always this small O remainder, and this was pointed out in a recent work of Josevich and Wyman, where they actually study products of spheres and get much stronger estimates on the remainder. But if you want something more than just small o, you might go back to the work of Berard and sort of contribute to more recently by Bontenot, where they prove that if the manifold has no conjugate points, then you can get a quantitative improvement in this remainder. And up until relatively recently, this was more or less, you know, the state of the art from the point of view of quantitative improvements, unless you're talking about very, very special manifolds like, you know, the torus or something like that. So you can show this logarithmic improvement on a manifold without conjugate points, but you didn't know a lot more about when you can prove some kind of quantitative improvement in the remainder. And so recently with Scheisse, we proved that, for example, and I'll go into more detail about what we actually can prove, but as an example, if you take any product manifold, again with the product metric, then you still have this logarithmic improvement. And I just want to point out that this type of manifold, of course, can have lots of conjugate points. There's no, you know, I have no restrictions on what the two factors are, just that they have two non-trivial factors. And so this is actually quite, it was surprising, at least to me, that this has not been at least written down. Whether it was known or not, I'm not sure. But as far as I'm aware, it wasn't in the literature. And I want to point out that this is not a consequence of just having the product of two lattices, or sorry, two sequences with Weyl asymptotics themselves. You can construct examples which don't even satisfy the small o remainder and are nevertheless sort of in each factor having the Weyl asymptotics. But the point so we want to go after these Weyl laws. We want to understand remainders in this setting. And one way that people think about this is to look at the spectral projection, which is just the projection onto the kernel of these this operator, where I take eigenvalues less than lambda square. And the spectral projector, of course, has a kernel which you can write down in terms of eigenfunctions. And you can rephrase, excuse me, the Weyl law in terms of an integral over the diagonal of the spectral projector, right? And this is one way of viewing the Weyl law is as asymptotics for the trace of the spectral projector. But you might ask for finer things. You might ask for example, pointwise estimates on the spectral projector, where again, you have some main term, which, okay, it's sort of natural that it's just removing the integral or the volume of the manifold here and getting the same kind of remainder. And of course, you can do more things. You can integrate over submanifolds, and you can do all sorts of games with the spectral projector and ask what you can say about the asymptotics. But the goal for us is, how do you obtain some kind of quantitative improvements that you might be able to check on a typical manifold? Okay, so that's how we want to think about this. How do we get a quantitative improvement that might work on a typical manifold? And again, so far I've only told you that there are quantitative improvements on say the torus or on manifolds without conjugate points. So those are very rigid geometric structures. So you probably don't want to be using that type of characterization. And so I want to give you an idea of how we prove things that I'm going to talk about. So an idea of what the techniques are, and then I'll tell you what the actual sort of results look like. And the idea is that the spectral projector, or more precisely a projector onto a short window, so you should think that this R of lambda is like 1 over log lambda, for instance. This thing is a quasi-mode on M cross M, and it's a quasi-mode for this operator, right? And sorry, this should not be a plus, but a times, but that's okay. And so what you want to do is you want to study quasi-modes of operators, and you want to study their behavior when you integrate them over a submanifold, in this case, the diagonal of M cross M, right? And so what I really mean is that when I hit this phi lambda thing with this operator, I get a small remainder where small means like that. And once you have that, you try to decompose. You think about this this number as an integral over this quasimode over the submanifold, namely the diagonal. And so this leads you, or this is one reason you might want to study integrals of quasimodes over submanifolds. And indeed, actually, sort of we came in this the other direction. So we studied integrals of quasimodes over the submanifolds, and then we realized that actually this was one way of viewing this. Okay, and the technique is what we've been calling the technique of geodesic beams, which is that you want to decompose your quasimode into geodesic beams, so into, in other words, pieces which are localized along short tubes, so short segments of a geodesic in a very thin tube. So this tube is some radius capital R of lambda, which you should think is, you know, roughly lambda to the minus delta for some delta less than a half. And these little pieces should be localized there. And you want to write your quasimode in this way, and then get an estimate on each piece, which you can work with. So by decomposing into these geodesic beams, which again are similar, very similar to Gaussian beams, you can get estimates on integrals over submanifolds. And I do want to point out why should it be a geodesic beam? And that's because what you want from these localizers is that they should have supports inside these small tubes, right? So they should, in other words, sort of micro-localize you to these small tubes. And you should, when you start with a quasimode, if you hit this thing with your operator, you should still have a quasimode. Okay, I'm lying slightly there. You should have a quasimode near the submanifold you're interested in, right? Because if you try to do this globally, then you're going to run into global obstructions on your manifold, and you want to try not to do that. And if you think about that for a second, you'll realize that this implies these things are localized. They need to follow geodesics, right? You can get the geodesic flow out of this equation by looking at what the commutator of P with chi Tj is. Okay, so this is just to give you a flavor of what goes into these results. And now let me tell you a little bit more carefully what the results look like. So we have what we're going to call a rate function on non-periodic sets, sublogarithmic rate functions. So all this is it's a function which is decreasing and bounded by log R inverse. Okay, so for the purposes of the talk, there's a little bit more to it, but for the purposes of the talk, it's a decreasing function which is bounded by log R inverse. And the way I want you to think about this function is that it tells you, okay, so if have fuzzy glasses on, so I've got blurry glasses on, and I can only understand where things are on my manifold up to scale R, how long can I keep track of things under the flow? That's what this rate function tells you. So if I have the blurry glasses on, which only allow me to resolve the manifold at scale R, how long can I track the geodesic flow? So that's how you should think about this. And then what we're going to look at is we're going to look at points that look like they're periodic with the fuzzy glasses on. So in other words, I take a ball of radius R inside S star M, and I've got my fuzzy glasses on. So all of these points look the same to me. I flow it under the geodesic flow, and I ask, does this tube thing come back and intersect the original ball? And if it does, I call that point periodic, and I put it into this set. And I only do this up to times below my sublogarithmic rate function. So again, I've got my fuzzy glasses on. I only can track things up to this time T of R, and I ask, do these two things intersect up to that time? And that means
Jeff, do you mean 1 over log R? Log R inverse is like...
No, I really mean log R inverse. Right, so R is small means the time goes to infinity.
Okay.
Yeah.
Okay, thanks.
No problem. So, and then what I'm going to do is I'm going to look at a subset of S star M, and I'm going to call it non-periodic if I have some volume control on this periodic set, again, where I've got the fuzzy glasses on. So things aren't literally periodic, they're somehow nearly periodic. They're periodic up to this blow up of scale R. And if you want to know what are some manifolds which are T non-periodic with this T, then you can think about product manifolds. You can think about, okay, manifolds with no conjugate points, but even manifolds with sort of no maximal self-conjugate points. So this means that not all of the geodesics should, or not all of the Jacobi field should vanish when you come back to the original point. I won't say more specifically what that means. You can do this for non-Zoll convex analytic surfaces of revolution. You can do this for some compact Lie groups, but these two were checked by Volovoy actually in the 90s. And actually here you can get substantially stronger non-periodicity. But in any case, in all of these cases, you have logarithmic improvements in the Weil law. And indeed, again, due to Volovoy, you can check that in these very special situations, you can do a bit better than that. You can get a polynomial. Okay, and so I want to try to explain one way you can try to check non-periodicity, which is by spreading of geodesics. So I'm going to do this sort of, try to schematically do this for product manifolds. And here's my product manifold, right? You've got an M1 and an M2. And what you imagine is you have, okay, here's my periodic geodesic. How can I realize that there aren't so many of those, right? There aren't so many periodic geodesics. There's a small volume, even if I have to blow this thing up by scale R, right? Even if I have to make it a little bit fatter. And the thing is, you imagine rotating the initial vector sort of up and seeing that as you rotate this, maybe when you come over here, you get some spreading, right? So, and if you do that, if you have that kind of spreading, then you can see that even if I just rotate a little bit over here, I'll be escaping the periodic set, right? I'll be no longer periodic if I rotate just a little bit. And so if you're on a product case, it's easy to check that you have this kind of spreading, because if you have a T periodic geodesic, then you can always write it as a product of two, excuse me, periodic geodesics, but now not with unit speed, but with some relative speeds to one another, cosine of theta 0 and sine of theta 0. And if you want to realize that these are part of a spreading family, you can just spin the theta. So you can just change the speed relative to one another. And it's not, so this, of course, provides the spreading. And you can see that indeed, this geodesic will be periodic if and only if the ratio between this cosine of theta and cosine of theta 0 is rational, right? So, or sorry, the tangent of theta, if you wish, and the tangent of theta 0. And indeed, you can sort of turn this into a more robust statement about how many nearly periodic geodesics there are up to some time at certain scales. So this is just to give you an idea of how you might think about checking the non-periodicity condition. So
is it kind of a Morse index, or, I mean?
No, I don't think it's anything that sort of fine, so right?
You are not looking at Jacobi fields, because Jacobi fields are supposed to track that, right? I mean,
so you can, we can do this by looking at Jacobi fields, right? But it's a very sort of local thing. There's no, I mean, I don't think you can see this from the Morse. I don't think you can see this from the Morse index, but okay, I'm not sure. Thanks. So in the last slide, I just want to give you an idea of what the sort of true theorems look like. So again, I've got my spectral projector, and I want to look at some sublogarithmic rate function and some submanifold, or some subset rather, of the manifold M. And I want to assume that this open subset is non-periodic. And what we can say then is that, sorry, let me do one more. So what we can say then is that if you don't take the whole trace, but rather integrate over some piece of the diagonal, say this U, then you still get this improvement in the expected asymptotics, okay? And so the reason this is sort of interesting is that you can really construct examples where you have a big periodic set. So you can, for example, take a sphere and leave the metric alone in this orange region here. And so, of course, all the geodesics which don't leave the orange region are periodic. You can put a tiny bump somewhere on your surface of revolution, and again, leave the sphere alone out here if you wish. And you'll realize that out here, this is aperiodic. So in the sense that I said. And so what this means is that you can get asymptotics for the integral over these green caps on your surface of revolution, which are, you know, substantially better than what you have for the sphere, and even though you have this big periodic set. And so, for instance, what this means is that if you do have large multiplicities, say, or near multiplicities coming from these periodic trajectories, then those guys can't really see very strongly the outside of this sphere. So that's sort of a neat consequence of this this asymptotic estimate. And so I will stop there and thank you for your attention.
Thank you, Jeff. Thank you very much. Other questions for Jeff?
I have a question and a remark. So one question, suppose you have a product manifold and you perturb the product metric a little bit, right?
Mm-hmm.
Can you say something nice? Because on the other hand, I guess you have to be a little bit careful, right? Because of the Hopf theorem. So if you have a non-flat metric on the torus, which is a product guy, right?
Yeah.
Then if you perturb a little bit, you will have conjugate points. So that may...
So we don't mind conjugate points, right? Conjugate points are not in principle a problem. However, you do have to be very careful about perturbing things when you're talking about these quantitative estimates for long geodesics, right? This is a rather delicate business, but the conjugate points as such are not an issue.
So you can improve things, let's say, I don't know, away from conjugate points or something, right?
So that's one version, but also, I mean, even the existence of the conjugate point doesn't rule out that you have some better asymptotics globally, right? I mean, it doesn't rule out that you have this non-periodicity.
I see. And another remark is, I think there are some recent papers by Zeldich and Goffers on like integrals of on restrictions of eigenfunctions, where he calls it, I think he calls it Fourier coefficients, right?
Yes,
Or rate of decay. So you look at the eigenfunctions on the manifold in which you restrict, and then you integrate.
Yes.
So can you combine like your methods and those?
Almost surely. Let me just say, almost surely, yes.
Okay.
But I mean, we haven't done it.
Okay, thank you.
Thank you, Dima. Is there anyone else who would like to ask a question? Okay, if not, let's thank Jeff again.